Hello everyone. Welcome to the second lecture of second week of this course. In this lecture, we will be primarily talking about the deep learning, machine learning techniques. To give a bit background, what we have done till now is that we have talked about what this course is all about, what are all the topics that we will be studying in this course. We have talked about different basic Earth observation tasks. We have talked about different sensors such as multispectral, hyperspectral, SAR. We will be coming back to them later and we'll be discussing those in much more details. However, right now we have basic background of those sensors. In case some of you are actually from the Earth observation background, maybe you have much more exposure to those topics. However, even if you are not from such background, you now have the basic working background on those sensors. And as we have also already mentioned, the course is mostly about deep learning for Earth observation. That is, from the next week onwards, from week 3 onwards, we will be mostly discussing different deep learning architectures, deep learning techniques for Earth observation. We'll be starting with CNN. We will briefly talk about, very briefly, LSTM and all, but not so much in details. Whereas towards the end of the course, the last few weeks, we will be talking about transformer, vision foundation model. Whereas separate from that natural flow, in this week, most of the rest of this week, we will be talking a bit about how remote sensing image or data analysis was mostly done. Let's say I will be giving this the year bracket as, like, let's say 2000 to 2010. So this is not an exact year bracket, but the kind of algorithms that we'll be discussing, 2000 to 2010, we can kind of say like that was the dominant time when they were applied. Obviously, we still see like some of these methods are used, like support vector machine. Like if you open, let's say, recent, like let's say like Iger's 2025's program details of what all paper was presented, you will still find like there are some papers on support vector machine. There are some papers using decision tree. However, right now, dominantly what we see is that mainly deep learning, like CNN or transformer-based architectures are used. Whereas if we go back, like let's say 2007, 2008, even 2012, 12, 13, 14, we see like dominantly SVM, decision tree, those kind of methods were used. Also, like one of the lectures of this week will be more focused on change detection, again talking about some of the more traditional change detection approaches such as change vector analysis. Again, I mean, right now probably they are not so much used, but they have contributed to forming the base for more recent methods such as deep change vector analysis or even like supervised IMS architectures as well. So how I see like rest of this week is like this. If let's say you have those exposure, like you have already done a machine learning course or like like those methods such as change vector analysis and all, you probably like, and of course if you're not doing this course for a certificate, if you're doing this course as a certificate, of course you should still watch all of these lectures, because otherwise probably it's difficult to answer the assignments and all. But if you're rather just like following this course not as a like to get a certificate, maybe like in that case, and if you have those background, maybe you can even skip these lectures. Whereas if you don't have much background of these topics, it's good to watch through these topics. It kind of forms a basic foundation, even though we don't repeat these topics so much in the subsequent weeks. So with this, let us start talking about pre-deep learning era. Support vector machine or its variants, they were one of the dominant machine learning paradigms in remote sensing. I mean, you can, like if you want, you can experiment different ways to actually validate this claim. Like you can open one of the popular IEEE journals on remote sensing, and you can see like, okay, what all papers were published, and not all of them are using machine learning as such back then. Even now, of course, not all of them will use machine learning. But among the ones which were using machine learning, how or which like method was used more, and you will see like support vector machine back then. Like if you think about 2007, 8, 9, 10, 11, it was quite dominant. So the usual pipeline used to look like this. You will use some kind of mechanism to extract feature. I mean, it could also be the case in some cases, like let's say we are working with hyperspectral images. It could also be the case that, okay, we don't probably even go for a feature extraction. However, most of the time we will use some kind of feature extraction, and one of the popular would be texture features. And there are like different mechanisms there also. So one popular way is the Haralick's texture feature. So if you are curious, you can read about these mechanisms. However, the key message here is that this feature extraction pipeline, this is sort of decoupled from the later classifier pipeline. Feature extraction is happening with this like kind of like, okay, like text, like if you're doing the Haralick's feature extraction, texture feature extraction, what's happening is that like we're using a set of like fixed equations and all. Those are not learned. Unlike later we'll see in the case of the CNN, where in a way like the feature extraction itself is like a coupled with the classifier. So with this usual pipeline, how shall we proceed? So here are like some examples to convince you that how SVM was indeed popularly used in the Earth observation data during those time. So the particular example you are seeing here is in the context of hyperspectral data, and the work which has been cited in the footnote. You can read the paper if you are curious. There we see that different multi-class classification strategies have been evaluated, such as one against all, one against one, and also some hierarchical tree-based strategies. So to give it a bit background, the support vector machine that we are soon going to, going to talk about more, like the algorithmically, we will see that this is more about binary classification. So given to class, we are trying to fit a hyperplane, whereas in the earth observation, most of the time we work with multi-class use cases, right? So in this case, how to extend this binary classification paradigm to multi-class, and there comes this one against all or one against one or such techniques, and we will be talking about them a bit in more details later. So this particular work we see is back from 2004. Similarly, another example, also again from 2004. What we see is again multi-class SVM applied on both multispectral Landsat 7 ATM plus data as well as hyperspectral data as well. So this particular work, they have shown experiments using multispectral, using hyperspectral, both, and their test areas included certain areas from eastern inland and central Spain, and their result showed that SVM achieved higher level of classification accuracy than the other compared ML approaches. So here you need to be careful that when we are talking about that, okay, SVM achieves high level of classification accuracy, this is in comparison to the ML other pre-DL ML approaches. So there were like so many other variations. This is another particular example from 2006 where SVM was combined with genetic optimization framework. Yet another interesting example from 2004 where they proposed, in the context of multispectral remote sensing image segmentation, active SVM. So what's happening is that, let's say you have a level data set and you use the SVM to now fit a hyperplane, right? So we said that we'll be talking about how to fit this hyperplane soon. Now let's say you have a large set of unlabeled data as well. What you can do is somehow, based on some kind of hypothesis, like kind of confidence estimation and all, you can say that, okay, this is the data I'm not so much confident about on this unlabeled data, I mean, and this data then needs to be, since you're not so confident about this particular data, you just send it to human expert to annotate, and those human expert annotations now can be again used to further fit your, like, further adjust the hyperplane using your SVM algo. Similarly, interestingly, semi-supervised methods were also devised using variants of support vector machine. The particular example you are seeing in the footnote is from 2010. So we have seen, like, the last few examples, most of them either talked about multispectral or hyperspectral images. You might be thinking, what about SAR? So it's not the case. This was not used in SAR. It was adopted for SAR image analysis as well, as you can see the example in the footnote. So with this, so we have till now what we have done is that we have kind of convinced ourselves that this is worthy to talk about support vector machine. Indeed, support vector machine was one of the dominant approaches used in the pre-deep learning era. And this is not just true for the earth observation, this was true for entire computer vision and its application areas as such. In the like when we actually start talking about deep learning, we will show how in the case of ImageNet dataset, the first time the challenge was released, what happened is that the winners were some kind of support vector machine variants. Only the next version of the computation, the CNN based approach, a particular CNN based approach emerged as winner. So yeah, I mean, the gist is that okay, we have convinced ourselves that okay, like support vector machine was indeed a dominant approach. So with this background, now let us start talking about support vector machine in more details. So support vector machine, this is a supervised learning algorithm primarily used for classification. What it does is it learns a decision boundary that separates the data from different classes. And the goal is to find the optimal separating hyperplane between two given classes. It's particularly effective for small to medium sized training data. So this is one very important aspect where, you know, like with the emergence of this ImageNet and all, there are other reasons as well, but this like the dataset size is one of the reasons, like okay, how the evolution happened from like, or the transition happened from support vector machine to the CNNs. So to talk a bit more about the idea of maximum margin. If let's say like, let's assume to start with our data is linearly, we are having two classes, our data is linearly separable. This would mean many hyperplanes can actually separate our linearly separable data. So think about, like we will see example, visual example soon. Think about before going to the next slides. I mean, right now we have not seen it pictorially, but just try to imagine yourself like some data from two classes in 2D plane. So then like the hyperplane, this in this case is just your line. And if your data is like linearly separable, you can probably like draw several such lines between these two sets of data. Now what we're saying special about SVM is that SVM will try to find not just any hyperplane, separating hyperplane. This will select the hyperplane with the largest margin from both classes. A larger margin generally leads to better generalization on unseen data. And we'll see soon what happens is that this optimal boundary, this is indeed decided by actually just a few training samples. It's not like, okay, like you really need to worry about all the training samples to pinpoint this optimal boundary. Yeah, so as I said like before, that try to visualize in your mind. So here now we are with some visual examples. We see data from two different classes. We see okay, they're nicely separable, and there we have drawn a line, right? Now the question arises is that, is this particular line, the left figure, the line that we are seeing, is this one the appropriate one or the best choice? The answer, if you think a bit, the answer is no, right? Why is the answer no? The line that you have seen here, it's not that challenging to observe that this is so much, we have drawn it so close to the class 2 and so far from the class 1. For this data, it's maybe fine, but now you sample some new data, and maybe now this still belongs to the class 2, but you end up classifying it to class 1. Similarly, we can also think about the figure in the right side. There, it's a bit different. Here what we are seeing is that the line in one side, it's so much approaching the class 2, whereas in the other side, it's so much approaching the class 1. In some sense, I will say that this particular example that we are seeing here is even worse than the left side example. And this will be if you think about this again, before going to the next slide, give it a moment to think about this, why I'm saying that this one, the right side one, this is worse than the left side one. The left side one has more or less the right orientation, as we see so. This right side one doesn't even have that. So maybe the left side one, we just move it a bit and we have the right hyperplane. Okay, not the case with the right side one. Okay, so with this background, now what we are looking at is our the hyperplane or the line, in this case to the example that we want to actually find. So let's say we have our data x1, x2, xn, and let's say we have the class labels either 1 or +1 or -1 for each of these xi. Okay, so we are saying, let's say these are my y is equal to 1, the red points, the blue points that you are seeing here, let's say these are y is equal to -1. Okay, now we have this hyperplane such that we can think that, okay, this satisfies the equation wtx plus b, okay, is equal to 0. So here it's probably clear to you already that x, we are seeing our data, this is coming in the vector form, w is coming in the vector form. So now we have another 2 also lines we have drawn here, or hyperplanes. So wtx plus b is equal to 1 and wtx plus b is equal to -1. What we see is that all my rate points, they either touch this wtx plus b is equal to 1 or they're in the the other side, right side of them. All my blue points, they are also either touching this wtx plus b is equal to -1 or they're to the left side of them. Also, we have this w here. Okay, it's shown more pictorially. So now, so this name, in the name you have seen already, support vector, you would be asking, right? Okay, what are the support vectors? So that's the definition that the points on the margin, these two margins that we have drawn, we'll be calling them as support vector. Now, what we're saying is that the vector defined by the weight W, this is perpendicular to the decision boundary. So this is a decision boundary, and the vector defined by weight W, we are saying this is perpendicular to this decision boundary. Why so? So to simply see this, you can think about two different points, x and x dash, both on this boundary. And we have seen this boundary, this satisfies this equation, right? Wtx plus b is equal to 0, which means both of these points x and x dash, they will satisfy this equation is equal to 0, and then you can just equate and cancel b, and you get this Wtx minus x dash is equal to 0. So this directly leads us to this conclusion that the vector defined by the weight W, this is perpendicular to the decision boundary. Now, let's say we choose some x minus such that my fx minus is equal to -1, and let's say we have some x plus be the closest point to x minus with fx plus is equal to +1. So we are choosing one point from this particular line, then another point such as it's closest to this x minus from this particular line, and they need not be one of these actual data points that you are seeing in in blue color or red color, okay, but you can take these 2 points, x minus and x plus. So what you can do is that you can then in that case write as x plus is equal to x minus plus RW. Now with this, what we can do is we wrote this x plus is equal to x minus plus RW, and we also know from the particular equations of those two lines, we also know that W dot x plus, okay, plus B, okay. So instead of WTX format, I am just writing it as more dot product format. So what we get is this is equal to +1. At the same time, this is in the other line, right? Other margin line. So this is equal to -1. Now this particular relationship x plus is equal to x minus something, you can actually fit in one of these lines. So you can substitute in one of these lines. This is exactly we'll be doing, and this is what we have done. Okay, so Wx minus plus Rw plus B is equal to +1. So this leads us, after some simple calculation, what we see is that we get a value of R expressed in the form of norm. Now what can we do with this value of R? We now calculate the margin, okay, the margin between these two lines that we saw. So this margin will be simply x plus minus x minus norm of this, which will be Rw of norm of this, and this leads to basically this. And this margin M is something, from the optimization point of view, this is something quite interesting, right? You will be probably trying to maximize this, right, margin. So this is the margin pictorially, okay. So what we are saying is that we will probably like to maximize this. Why maximize this? Because maximizing this means that we have good distance between this y is equal to 1 and y is equal to -1, these two particular classes, right? At the same time, you have to understand that for yi is equal to 1, we are always satisfying this equation wtxi plus b is either is equal to 1 if it is on this line, or if it is like to the other side of this line, then it is wtxi plus b is greater than 1. Okay, so which means yi into wtxi plus b is greater than equal to 1. Whereas on the other side, like if we think about the yi is equal to minus 1 particular case also, this wtxi plus b is less than or equal to minus 1. If we multiply again yi and wtxi plus b, it's again greater than equal to 1. So no matter what, we are getting this yi wtxi plus b greater than equal to 1. So these are the two things that we have found till now. We have found a particular value for this margin m, and we said that okay, maybe we would like to maximize this, and we have now found another this constraint in the terms of yi wtxi plus b. Now let's combine them together. So probably we are trying to find a w such that we are trying to maximize this, or just take the like just invert this and you are trying to minimize this. Okay, half of norm w square. Okay, subject to the particular constraint that we just derived, yi w dot xi plus b is greater than or equal to 1 for all I. And this must be clear by now to you that okay, like the particular examples that we saw, the examples that matter to us mostly are like the ones which are on the margin, right? Now, with this background, let us move ahead to something called soft margin SVM. Previously, we discussed this. We assume that okay, our data is nicely linearly separable. However, what happens is that real world data sets are often not perfectly linearly separable due to noise, due to overlapping classes. In such cases, a hard margin SVM fails when even a single, for example, violates the linear separability. And here, the soft margin SVM comes into play. This allows a limited number of margin violations and misclassifications. So what we see is that we say two things, right? One is margin violation. So this red example that you see here, this is a nice demonstration of margin violation. So with this particular decision boundary, we are not really misclassifying this, we are just violating the margin. So this was the margin, it's not to the other side or on the margin, it's rather on this side of the margin. Whereas we said that okay, it also supports now misclassification, right? And this misclassification case is one which we have seen with this blue example, right? So this is indeed on the other side of our decision hyperplane, and so this is misclassified. So what we do is mathematically is that we will introduce this epsilon so greater than or equal to 0, such that right now we have wtxi plus b is greater than or equal to 1 minus this epsilon, wtxi plus b is less than or equal to minus 1 plus this epsilon. Okay, and with this, what will happen is our optimization, this will become now the minimize of like half norm w square. Not just that, plus we are having an additional term c summation of this eta I, okay, subject to this particular equation in the terms of yi wxi plus b also changes. Okay, you can easily verify like why this will satisfy, and all the epsilon i's are greater than or equal to 0, right? So here one important aspect to note is this c, right? We have added this particular additional term in our minimization objective with this c multiplier. So this c is a regularization parameter here that controls the trade-off between maximizing the margin and minimizing the training errors. A large c, what will happen is that this will assign a high penalty to misclassified samples, resulting in fewer training errors but an error margin. A small c will allow more margin violation, leading to a wider margin and potentially better generalization. So with this, we'll take forward our discussion in the next lecture. We'll stop here. Thank you.